In 2003, a heavy-duty Chevrolet van rolled down an assembly line carrying the final factory-installed Gen I small-block V8, quietly ending a 48-year run of the exact cast-iron architecture that built American hot rodding. Since 1955, General Motors had cast over 100 million of these blocks. It powered muscle cars, pickup trucks, and marine inboards. But its true scale existed outside the dealership. For American mechanics, dirt track racers, and weekend builders, the small block was a universal currency. A machine so standardized that parts were swapped in junkyards and driveways, coast to coast. The paradox was absolute. By 2003, the original iron block was too inefficient to survive tightening emissions rules and the rise of modern, software-controlled aluminum V8s. The factory had to move on. Yet the engine was too deeply embedded in American garage culture to actually disappear. But the real story of the small block Chevy is not only the story of its final factory run, it is the story of how a single piece of cast iron became the universal language of American horsepower, and what happened when the industry could no longer afford to speak it. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Detroit, Michigan, in 1954, just before the rules of American horsepower changed forever. In 1954, Detroit, Michigan was building the machines that would fill an expanding network of American highways. The country was moving outward into new suburbs, and distance required speed. But Chevrolet, General Motors' highest volume division, had a mechanical problem. For a quarter of a century, the brand had relied on the stove-bolt straight six, a heavy, reliable, but slow six-cylinder engine arranged in one long line. It was a tractor engine in a passenger car designed for an era when roads were rough and speeds were low. The American horsepower landscape was strictly divided by price. If a buyer wanted real power, they had to pay for a Cadillac or an Oldsmobile, which had introduced modern overhead valve V8s, engines with valves in the cylinder head operated by push rods years earlier. Ford had democratized the V8 back in 1932 with the flathead, an engine design where the valves sit in the block rather than in the cylinder head. But by the early 1950s, the flathead was thermally and structurally exhausted. It ran hot, it struggled to breathe, and it had reached the absolute limit of its mechanical architecture. America needed a new baseline for power. It needed an engine that was cheap enough for a young mechanic to buy, light enough to balance a car, and easy enough for a factory to cast by the millions. Enter Ed Cole, Chevrolet's chief engineer. In 1952, Cole looked at the blueprints for a proposed Chevrolet V8 and threw them out. The prototype was too heavy, too complex, and too expensive. Cole understood that a true American engine empire could not be built on a heavy block. He gave his engineering team a near-impossible mandate: design a completely new lightweight V8 in just 15 weeks for the 1955 model year. The result was the 265 cubic inch V8. To understand why this specific engine changed the American garage forever, you have to look at what the engineers left out. Early V8s from other manufacturers were massive chunks of iron, requiring complex cores and heavy casting techniques to form the block, the main engine structure that holds the cylinders and major internal parts. Cole's team utilized greensand core molding, allowing for thin wall casting. They poured the cast iron so precisely that the engine block was entirely devoid of unnecessary metal. The 265 V8 weighed roughly 150 pounds less than the stove-bolt 6 it replaced, yet it produced dramatically more power. The base model generated 162 horsepower, a measurement of how quickly an engine can do work. With an optional 4-barrel carburetor, a device that mixes fuel and air before it enters the engine, it made 180 horsepower. But the brilliance of the 265 was its internal simplicity. Traditional overhead valve engines used heavy, expensive rocker shafts to actuate the valves. The Chevrolet engineers deleted the shaft entirely. Instead, they used independent, stamped steel rocker arms that pivoted on simple ball studs. It was a friction-reducing, high-revving stroke of genius that cost pennies to manufacture. They also eliminated external oil feed lines to the top of the engine. Instead, oil was pumped directly through hollow push rods. To meet the anticipated demand, Chevrolet had to rethink its foundries. The engine was not just designed for the driver, it was designed for the machining line. The block was cast with open spaces that allowed the casting sand to be easily shaken out after the iron cooled. At the Flint engine plant in Michigan and the Tonawanda engine plant in New York, the assembly lines moved at a staggering pace. By the end of 1955, Chevrolet had produced over 1 million cars equipped with the new V8. This volume was critical. An engine cannot become a cultural default if it is rare. It must be everywhere. When the 1955 Chevrolet Bel Air hit dealership floors, it was marketed as the hot one. It changed the brand's image overnight. The 265 V8 turned a conservative family sedan into a machine that could dominate a stoplight drag race and cruise effortlessly at modern highway speeds. However, the true origin of the small block empire did not happen on the pristine tile of a Chevrolet showroom. It happened a few years later, in the greasy bays of American repair shops, machine sheds, and dirt track garages. Mechanics and hot rodders, who had spent decades shaving metal off Ford flatheads just to gain a few horsepower, opened the hood of the '55 Chevy and saw something entirely different. The engine was remarkably compact. It was easy to work on. The distributor was mounted conveniently at the top rear of the engine, protecting it from road splash. The spark plugs were easily accessible above the exhaust manifolds. More importantly, it was modular. As Chevrolet began pumping these engines out by the millions, an ecosystem of parts began to form. Because the block was so simple and the manufacturing tolerances so tight, a mechanic in rural Ohio or a racer in Southern California realized they could swap cylinder heads, intake manifolds, and carburetors with basic hand tools. It did not require a machine shop to make it go faster. It only required a wrench, a parts catalog, and a weekend. The 265 cubic inch V8 proved that Detroit could manufacture high performance at an industrial scale. The factory had solved the problem of building a better engine for the American highway. What they did not realize was that they had just handed the American mechanic a universal tool. By 1957, Chevrolet engineers realized that the original 265 cubic inch V8 was not at its physical limit. It was merely a foundation. To extract more power, they increased the bore, the diameter of the engine's cylinders, expanding the overall displacement to 283 cubic inches. This new engine became a legend not just for its physical size, but for how it breathed. That same year, guided by legendary engineer Zora Arkus Duntov, Chevrolet introduced the Ramjet mechanical fuel injection, a system that sprays fuel into the engine more precisely than a traditional carburetor, relying on engine vacuum and mechanical linkages rather than electronics. Equipped with this advanced fuel system, the 283 achieved a mythological benchmark in American engineering: 1 horsepower per cubic inch. At exactly 283 horsepower, it was a marketing triumph that dominated trade magazines and showroom windows. But the true breakthrough of the Chevrolet small block did not happen on the pristine tile of a dealership. It happened in the salvage yards, the dirt track pits, in the independent machine shops scattered across the country. By the late 1950s, the first wave of 1955 and 1956 Chevrolets were crashing, rusting out, or finding their way into American junkyards. Wrecked passenger cars became mechanical organ donors. A young mechanic in Southern California or a farmer in the Midwest could walk into a salvage yard, hand over $50, and pull a used small block out of a wrecked Bel Air. They would then drop that compact, lightweight iron block into the frame rails of a 1932 Ford or a weathered pickup truck. This was the engine swap, the practice of removing a vehicle's original motor and replacing it with a completely different, often more powerful, power plant. The small block was uniquely, almost accidentally perfect for this American ritual. Older V8 engines, like the Ford Flathead or the early Chrysler Hemis, were massive, wide, and incredibly heavy, often requiring extensive cutting and welding to fit into older frames. The Chevrolet V8, by contrast, was narrow. Its exhaust ports pointed straight down, easily clearing the steering columns of older chassis. It utilized a simple front mount system. It looked as though it had been designed specifically to be stolen from a modern car and bolted into an old one. As millions of these engines poured onto American highways, a massive parallel economy formed around them. The aftermarket, the secondary industry of independent companies building parts to upgrade, modify, or repair a machine after its original sale, quickly realized that the Chevy Small-Block was not just another engine. It was a gold mine with a captive audience of millions. In the 1960s, a weekend builder did not have to rely on General Motors for performance. They could open a thick mail-order parts catalog and order an aluminum intake manifold from Edelbrock, designed specifically to bolt straight onto the Chevy V8. They could buy a high-performance carburetor from Holley to sit on top of that manifold. Companies like Iskandarian, widely known as Iski, and Crane Cams began grinding custom camshafts, the internal shaft that controls exactly when and how far the engine's valves open, allowing the cast iron block to breathe deeper and rev much higher than factory specifications ever intended. This massive ecosystem thrived because of one defining engineering choice: extreme interchangeability. Unlike other American automakers, who frequently introduced entirely new engine families that required completely different parts, Chevrolet refused to abandon the architecture of the 1955 block. They kept the bore spacing, the exact distance between the center of each cylinder, identical year after year. They kept the bell housing bolt pattern, the mounting points where the rear of the engine connects to the transmission, exactly the same. This meant a builder could take the high-flowing cylinder heads from a wrecked 1964 Corvette and physically bolt them onto a weathered 1955 truck block. A water pump from a station wagon could fit a drag racer. A starter motor from a heavy-duty delivery van could crank a hot rod. The engine was entirely modular. It was mechanical Lego. In an American garage, this changed the fundamental math of mechanical power. If a racer blew a head gasket, the vital seal between the engine block and the cylinder head, on a Friday night at a local dirt track in Ohio, they did not have to wait weeks for a specialized component to arrive from a Detroit warehouse. They could drive to any local auto parts counter on a Saturday morning, ask for a Chevy Small-Block gasket, and the clerk would pull a cheap cardboard back part off the shelf that fit 10 million different vehicles. That part's availability democratized horsepower. It meant that going fast no longer required deep wealth or a specialized racing team. It only required a wrench, a parts manual, and a weekend in the driveway. Because the block was incredibly cheap to mass produce, highly reliable under continuous load, and universally understood by American mechanics, its influence soon spilled over the boundaries of the automotive industry entirely. Marine companies like Mercury Marine and Chris-Craft began marinizing the small block, adapting it to become an inboard marine engine, a power plant mounted deep inside a boat hull to drive a propeller. The same V8 architecture that powered a family sedan on the highway was now pulling water skiers across Midwestern lakes, echoing out over the water on summer afternoons. Agricultural and industrial suppliers realized the same cast iron block could run a heavy-duty irrigation pump in the Central Valley of California or power a stationary generator behind a hospital. It was cheap to buy, cheap to run, and impossible to break without warning. The engine was no longer just a Chevrolet product. It had become a piece of public infrastructure. By the late 1960s, the Chevrolet Small Block was no longer just an engine. It was an industrial empire of cast iron. The original 265 and 283 cubic inch displacements had evolved and expanded. In 1962, Chevrolet introduced the 327 cubic inch version, a high-revving powerhouse that cemented the Corvette's performance reputation on the street and the track. But the absolute peak of this mechanical empire arrived in 1967 with the introduction of a displacement that would become synonymous with American automotive culture itself, the 350 cubic inch V8. The 350 was the perfect physical balance of bore and stroke. It produced massive low-end torque, the twisting force that gets a heavy vehicle moving from a dead stop, while maintaining the compact, lightweight packaging of the original 1955 design. It was instantly installed across the entire General Motors passenger fleet. It powered the newly launched Chevrolet Camaro. It went into the massive, heavy Caprice and Impala station wagons that hauled suburban families across the expanding interstate highway system. But the glory and scale of the small block was not defined merely by muscle cars. It was defined by sheer volume and relentless utility. The 350 became the default heartbeat of the American workday. It was dropped into millions of Chevrolet CK Series pickup trucks, working in dirt, mud, and snow. It powered the heavy-duty step vans that delivered bread, milk, and parcels to Midwestern neighborhoods. It sat beneath the doghouse engine covers of U-Haul rental box trucks, trusted to carry families moving their entire lives across the country without a mechanical failure. In an America where an engine could decide whether a farmer's irrigation pump ran through the night, a local delivery truck met its route, a drag racer made it down the quarter mile, or a family boat returned safely to the marina, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. The small block 350 delivered that trust at a scale and price no competitor could match. At peak production, General Motors was casting these engine blocks by the tens of thousands. The foundries in Tonawanda, New York, and Flint, Michigan operated around the clock. Factory workers shook casting sand from red-hot iron and machined the cylinder bores with relentless, standardized precision. The engine was so ubiquitous that it created its own economic standard. Walk into any American automotive swap meet in the 1970s, like the massive Pomona swap meet in Southern California or a local county fairground gathering in Ohio, and you would see the reality of this scale. A bare 350 engine block, the heavy iron casting without any internal moving parts, was treated like cash. It was a universally accepted currency. A builder could trade a solid 350 block for a set of racing tires, a rebuilt transmission, or a heavy-duty rear axle. Everyone knew what it was, everyone knew how to machine it, and everyone knew there would always be a buyer. The service network that surrounded this engine was unparalleled. A truck driver or a traveling salesman whose Chevy V8 developed a misfire in a rural town did not have to panic. Every local auto parts counter, every independent garage, and every small-town dealership stocked parts for the Chevy Small-Block. A mechanic could rebuild a 4-barrel carburetor on the tailgate of a pickup truck. A water pump could be replaced in a diner parking lot in under an hour. The engine's architecture was so familiar that an entire generation of American teenagers learned the fundamentals of the internal combustion engine simply by tearing down a small-block Chevy in a high school auto shop or a suburban driveway. They learned the firing order by heart, 184-36572. That exact sequence of numbers became a cultural password among American mechanics. The small block had conquered the highway, the drag strip, the dirt track, and the American driveway. But to understand the sheer magnitude of its dominance, you have to look at where the iron went after it left the road. To understand how deeply the Chevrolet small block penetrated American culture by the 1970s, you have to look away from the General Motors assembly lines and look at the mail-order catalogs that landed on millions of kitchen tables. Companies like Summit Racing Equipment and Jegs High Performance built massive national empires entirely around supplying parts for this single-engine architecture. For an American teenager building a car in a suburban driveway, these catalogs were wish books. Every page offered a new way to manipulate the exact same cast-iron block. You could buy an aggressive camshaft to change the idle from a smooth hum to a violent, aggressive chop. You could buy an aluminum cylinder head, the upper part of the engine that helps seal the cylinders and contains the valves, to reduce weight and increase airflow. The engine had evolved from a proprietary corporate product into an open-source mechanical platform. This open platform dominated American motorsports. If you went to a Saturday night dirt track in Ohio, Pennsylvania, or the Carolinas, the air did not just smell like unburned gasoline and tire smoke. It vibrated with a very specific frequency. The vast majority of sprint cars and modified stock cars on those tracks were running some variation of the Chevy Small-Block. The reason was pure economics. A dirt track racer could pull a junkyard, 350 cubic inch block, machine it locally, and install a heavy-duty forged crankshaft, the rotating shaft that turns the up and down motion of the pistons into rotational power, along with aftermarket connecting rods, the parts that link the piston to the crankshaft. For a fraction of the cost of a specialized racing engine, a weekend mechanic could build a 400 horsepower machine that could survive being held at its absolute redline, the maximum safe rotational speed of an engine, lap after lap. If the engine did blow up, it was not a financial tragedy. The racer simply went back to the salvage yard on Monday, bought another bare block for $50, and started rebuilding for the next weekend. The small block was disposable, yet infinitely rebuildable. This level of extreme accessibility made the small block the default answer to almost every mechanical question in America. When a hot rodder wanted to modernize a 1930s Ford coupe, they did not use a Ford engine. They swapped in a Chevy 350 because the parts were cheaper and the mounts were simpler. When a custom boat builder needed reliable inboard power, they chose the Chevy V8. The engine had become the mechanical equivalent of a 2x4 piece of lumber or a Phillips head screw. It was a standardized unit of American industry. By the time General Motors reached the height of its production, the small block Chevy had powered tens of millions of passenger cars, fleets of municipal school buses, countless rural water pumps, and a massive percentage of the American aftermarket. It had taught generations of mechanics how to measure tolerances, how to set ignition timing, and how to understand the physical relationship between fuel, air, and spark. The block was cheap, the power was proven, and the formula seemed invincible. But outside the garage, the rules of American engineering were about to change. The fall of the original Chevrolet small block did not begin with a bankruptcy, a factory closure, or a sudden mechanical failure. It began with a piece of paper in Washington, D.C., a shift in gasoline chemistry, and a nearly invisible crack in the foundation of American automotive engineering. In 1970, the United States passed the Clean Air Act, setting strict new limits on tailpipe emissions. At the same time, General Motors made a sweeping corporate mandate. By 1971, every engine across every division had to be capable of running on low-lead or unleaded gasoline. Lead had been used for decades to boost octane and prevent engine knock, but it was highly toxic and incompatible with the upcoming emissions hardware. To make the small block run safely on this new fuel, Chevrolet engineers had to drastically lower the engine's compression, the squeezing of the air and fuel mixture inside the cylinder before combustion. For a mechanic or a hot rodder, compression was the easiest path to horsepower. When you lower it, the engine loses its explosive punch. The drop was sudden and severe. The legendary 350 cubic inch V8, which just a few years prior had been proudly advertised at over 300 horsepower, was suddenly choked. By the mid-1970s, a base model 350 V8 installed in a heavy Chevrolet Impala station wagon was struggling to produce 145 horsepower. To the American driver pulling onto a fast-moving interstate, the change was immediately physical. The engine sounded exactly the same. The heavy iron block vibrated with the same familiar frequency. But when the throttle was pressed, the deep mechanical thrust was gone. The machine was working harder to do much less. This was the brutal reality of Force 3: regulation, emissions, fuel economy, and certification. The rules of American power had changed, and the 1955 cast iron architecture was suddenly caught on the wrong side of history. The small block was fundamentally a product of an era when gasoline was cheap and efficiency was an afterthought. It was an overhead valve pushrod engine with 2 valves per cylinder. It made power through displacement, the total volume swept by the pistons inside the cylinders, rather than through high-efficiency airflow. When the oil embargoes of 1973 and 1979 sent fuel prices skyrocketing and created lines at American gas stations, the small block's thirst became a massive corporate liability. To keep the millions of V8s legal and viable, General Motors began bolting on a complex web of emission systems, equipment designed to reduce pollutants from engine exhaust. The once clean, simple engine bays of American pickups and passenger cars were suddenly buried under a chaotic maze of vacuum hoses, smog pumps that injected fresh air into the exhaust, and exhaust gas recirculation, EGR valves that fed hot exhaust gases back into the intake manifold to lower combustion temperatures. In 1975, the catalytic converter, an exhaust device that helps convert harmful gases into less harmful emissions, became standard equipment, acting as a massive bottleneck to the engine's ability to breathe. In the suburban garages and independent repair shops across America, this transition caused a massive cultural fracture. The mechanics who had spent the 1960s tuning small blocks with a simple timing light and a flathead screwdriver now opened the hood to find an impenetrable nest of brittle plastic lines and early analog sensors. If a single vacuum hose cracked from engine heat, the engine would idle erratically, hesitate under acceleration, and fail state inspection. The extreme simplicity that had made the small block a piece of public infrastructure was rapidly disappearing. The engine block was still a solid piece of iron, but the ecosystem attached to it had become fragile. Chevrolet tried to adapt. In the 1980s, the carburetor, a mechanical device that mixes fuel and air, could no longer provide the precise fuel management required by tightening federal emission standards. General Motors introduced throttle body injection at a TBI, an early electronic system that essentially replaced the carburetor with a pair of computer-controlled fuel injectors sitting on top of the intake manifold. Later, they introduced tuned port injection, TPI, a visually striking system that routed air through long aluminum runners to boost low-end torque. These fuel injection systems restored some of the drivability and reliability that the smog era had stolen. A late 1980s Chevrolet pickup truck with a fuel-injected 350 would start reliably on a freezing Midwestern morning without the driver having to pump the gas pedal. It met emissions. It returned slightly better fuel economy. But these were ultimately just technological band-aids applied to an aging skeleton. The physical limitations of Ed Cole's 1955 design were finally becoming impossible to ignore. The iron block was too heavy for a market that demanded lighter, more fuel-efficient vehicles. The cylinder heads, constrained by the original bore spacing, could only flow so much air. General Motors was spending tens of millions of dollars engineering complex intake manifolds, computerized ignition curves, and restrictive exhaust systems just to keep the legacy engine compliant with federal law. They were fighting the basic physics of cast iron. The factory was doing everything it could to keep the original architecture alive. But inside the engineering labs in Detroit, the reality was already clear. The original small block was running out of time, and the replacement would have to abandon the past entirely. In 1992, General Motors made one final attempt to drag the 1955 cast iron architecture into the modern era. They released the Gen 2 LT1. It was heavily revised, featuring reverse flow cooling that sent cold coolant to the cylinder heads first, allowing for higher compression without detonation. But beneath the surface, it still shared the fundamental 4.4-inch bore spacing of Ed Cole's original 265 V8. It was a brilliant stopgap, but it was incredibly complex. It relied on a highly sensitive optical distributor, the OptiSpark, mounted directly behind the water pump where it was vulnerable to moisture. The engine was no longer the simple, forgiving machine that American mechanics had fallen in love with. The aftermarket struggled to adapt, and the factory knew that a cast iron block engineered during the Eisenhower administration could not meet the fuel economy and emission standards looming in the 21st century. The true executioner of the Gen Y small block was not a foreign competitor, an oil crisis, or an electric vehicle. It was Force 5, convenience and technological displacement, coming from inside its own house. In 1997, Chevrolet introduced the C5 Corvette, and with it, the Gen 3 V8, universally known as the LS. The LS completely abandoned the 1955 architecture. It featured a deep-skirt aluminum block for extreme rigidity, a revised firing order, symmetrically matched intake ports, and individual ignition coils for every single cylinder. It was drastically lighter, ran cleaner, and produced massive horsepower with absolute reliability. For the first time in 42 years, the top-tier Chevrolet performance engine shared zero interchangeable parts with the original small block. Almost overnight, the American hot rodding landscape shifted. Builders, dirt track racers, and garage mechanics who had spent decades mastering the 1955 iron block suddenly realized a harsh truth. A junkyard 5.3-liter LS truck engine could make more power with a simple computer tune than a heavily modified Gen I 350 could make with thousands of dollars in aftermarket parts. Open a Summit Racing or JEGS catalog in the early 2000s, and the shift was visible on the page. The front sections were entirely taken over by LS components. The Gen I parts, once the undisputed king of the industry, were quietly pushed toward the back. The LS was the new universal currency of American speed. The Gen I was instantly relegated to legacy status. Stripped of its performance crown, the original small block retreated to the industrial trenches. Through the late 1990s, General Motors updated the 350 into the Vortec 5700, internally designated as the L31. It received heavily revised, high-flowing cylinder heads that were among the best the factory ever cast for the Gen I. It was no longer a sports car engine, it was a pure workhorse. It was bolted into Chevrolet Silverado pickups, Tahoe SUVs, and commercial chassis. It still did exactly what it was designed to do, haul heavy loads across the American highway without complaining. But the walls continued to close in. In 1999, the new LS-based Vortec engines replaced the Gen Y in Chevrolet's highly profitable light-duty pickup trucks. The old iron block lost its place in the American driveway. It retreated one step further, finding refuge in the heavy-duty fleet market. The Gen Y survived in the engine bays of the Chevrolet Express and GMC Savannah commercial vans. Vehicles bought by plumbing companies, delivery fleets, and electricians who prioritize cheap parts and known maintenance schedules over high-tech efficiency. It also survived at the boat docks. Marine companies like Mercury Marine and Volvo Penta continued to buy the bare blocks to power inboard ski boats and cruisers, simply because the tooling was entirely paid for, and the heavy iron block was practically indestructible under constant marine load. But even in the commercial and marine sectors, the math eventually failed. The cost of manufacturing two completely different V8 architectures, one for modern passenger vehicles and one for aging fleet vans, no longer made financial sense. The emissions rules were tightening again. The old iron block, with its traditional push rods and heavy reciprocating mass, simply could not be tuned to burn fuel cleanly enough to satisfy federal regulators and corporate fuel economy standards. In 2003, the final order was fulfilled. Inside a General Motors assembly plant, a heavy-duty van received the last factory-installed Gen I small-block V8. There was no grand ceremony. There was no parade for the machine that had powered the American century. The factory line simply moved on to the next generation of aluminum and software. The engine still ran. The factory orders stopped. The emissions rules tightened. The racers moved to the LS. The hot rodders bought aluminum. The catalogs changed pages. The assembly lines retooled. The iron block was retired. The factory moved on to aluminum, software, and the future. But the millions of cast iron blocks left behind refused to be thrown away. The factory assembly lines in Tonawanda, Michigan, and Flint retooled for aluminum blocks and individual ignition coils, but the original cast iron small block refused to die cleanly. It simply changed its distribution model. General Motors understood that while the modern automotive market demanded the efficiency of the new LS architecture, the American garage still demanded the heavy, familiar iron of the 1955 design. The engine found its afterlife in a wooden box. GM Performance Parts began packaging brand new, factory-cast 350 cubic inch engines and shipping them directly to local speed shops, independent mechanics, and residential driveways. This was the crate engine, a complete, ready-to-run power plant delivered on a shipping pallet, requiring only fuel and spark to operate. The original small block effectively built the modern American crate engine industry, allowing a restorer in rural Texas to drop a brand new 0-mile 350 into a rusted 1968 pickup truck without ever having to visit a salvage yard. But the true legacy of the Gen I small block is not found in a corporate catalog. It is found in the sprawling, decentralized network of American preservation. Walk into the massive Pomona swap meet in Southern California or a local county fairground in Ohio on a Sunday morning, and you will still see the architecture everywhere. You will see rows of used aluminum intake manifolds, boxes of stamped steel rocker arms, and bare iron blocks sitting on folding tables, waiting to be traded. You will find thousands of oil-stained, dog-eared Haynes and Chilton service manuals, the physical books that taught an entire generation of American teenagers the firing order of 1-1-8-4-3-6-5-7-2. The aftermarket community that grew up around this engine never truly abandoned it. While the high-budget racing teams and modern hot rodders migrated to the computerized LS platform, the original small block became the domain of the traditionalist, the weekend father and son build, and the grassroots dirt track racer who still preferred the mechanical simplicity of a carburetor and a timing light. There is a strange, surprising footnote to the end of this empire. As American factories transitioned to modern technology, General Motors shifted the casting of the original small block to a massive foundry in Toluca, Mexico. For decades, the engine that defined American hot rodding, the very symbol of Detroit muscle, was quietly poured and machined south of the border, churning out millions of replacement blocks for the marine and aftermarket sectors long after the American plants had moved on to the future. The sheer volume of iron produced means that, mathematically, the world will likely never run out of Chevy 350 parts. But preservation is not the same as relevance. Why does a heavy, inefficient, two-valve pushrod engine from 1955 still matter in an era of software-controlled hybrid systems and electrified powertrains? This is not just nostalgia. A 1969 Chevrolet 350 engine block sitting on a steel stand in a Midwestern machine shop is a physical argument about a vanished era of American manufacturing. It is a monument to a time when industrial power was designed to be modular, accessible, and open source. It proves that America once built machines that were explicitly designed to be taken apart, understood, and fixed by the people who owned them. Today, opening the hood of a modern American vehicle reveals a sea of plastic covers, sealed electronic modules, and proprietary software that requires a dealership laptop to diagnose. The modern driver is a user of technology locked out of the mechanical process. But the original small block represented a totally different relationship between the driver and the machine. If a component broke, you did not replace the vehicle. You drove to the parts counter, bought a cheap replacement, and fixed it in the driveway with a wrench and a basic understanding of physics. The engine rewarded mechanical curiosity. It democratized horsepower. The Chevrolet small block did not just power the highway, the farm, the delivery fleet, and the boat dock. It taught an entire country how internal combustion worked, transforming millions of ordinary Americans into capable mechanics. It was the ultimate industrial tool, heavy, forgiving, interchangeable, and endlessly rebuildable. The industry eventually had to leave it behind. The emissions rules tightened, the fuel efficiency mandates forced a redesign, and the market demanded a level of technological convenience that cast iron simply could not provide. The factory moved on, and the world the small block was built to power was fundamentally rewritten by software and aluminum. Yet somewhere in an American garage, a cast-iron Chevrolet 350 still sits bolted to a red engine stand, the chrome valve covers catching the overhead light, a paper gasket waiting on the workbench, ready for a Saturday morning that will always sound exactly the same. See you in the next one.